These are the notes on summarizing the trends from your periodic trend lab. You should have already on your own completed day 1, which is looking at the reactivity trends in stations 1 through 4. You also should have completed the pivot on periodic trends. That looks at stations 5 through 7. And then you should have tried summarizing your findings on your lab sheet on your own. We're going to go through and do a quick overview and label your periodic table, just so that then you are prepared for that periodic trends lab assessment that you are going to use your lab sheet to complete. You do not need to submit your lab sheet to anywhere on Schoology. As we're diving into these, we just want to remember our vocab. So we're focusing on valence electrons, which are those electrons that are in our outermost shell or their highest energy level. Those are what influence reactivity, and those are things we're going to use to compare. With reactivity, we want to discuss octets. So how can an atom become stable, getting to those 8 electrons, whether by gaining electrons or losing? We also need to discuss Coulombic force, which is that attraction or repulsion of particles because of their electric charge and proximity. Because we're dealing with those protons, which are positive, and our electrons, which are negative, we're often talking about that attraction in these types of problems. Proximity, we are going to use energy levels, so that distance from the nucleus. Higher energy levels are farther from the nucleus, lower energies levels are closer to the nucleus. If we are comparing proximity. For electric charge, we're comparing that if the elements you're comparing are in the same energy level. And we want to compare the protons. How are we changing how many positive protons we have that might be influencing that Coulombic force? And with those CERs, you have some practice of using CERs for the first 4 stations. Make sure to talk to your teacher if you have any questions. There are some some of those CERs kind of have that evidence laid out for you, how you might structure them, but making sure then you're using our vocab to make those connections as you're explaining those trends. See the atomic stability notes or station 1 for that example of the format for those CERs. All right, so you should have your lab sheet out. And your periodic table, we're going to label those, and hopefully after these notes, you are prepped to do that lab assessment. In the first 2 stations, we talked about the alkali metals, so group 1 and group 2 with that. And those should have shown us that when we're looking at metals, we saw that reactivity increased as we went down. When we're labeling these, our arrowhead is going to point to that increasing reactivity. And so that reactivity is increasing as you are moving down in that group or moving down those periods. So increasing for metals as we increase energy levels. So adding that to your periodic table. We then also should have seen that in station 3 now, the reactivity for metals. As we move to the left on our periodic table, that reactivity is increasing. So that's a trend that you should have shown. In your explanations of this, we should see that because our Coulombic force is going to decrease as our energy levels move farther away from the nucleus, it's easier for those electrons to be removed. Also, as we move closer to only having 1 valence electron, we need to lose less electrons to get to an octet. But also, if we look at, let's say, boron, which has 5 protons, and beryllium, which has 4, beryllium has less protons, so it is going to have a weaker Coulombic force than boron. So it's easier for beryllium to lose those 2 valence electrons to get to that full octet. So that Coulombic force does decrease as we move to the left in a row. So have that reactivity for metals on your periodic table, labeling that. Now, looking at our non-metals, the halogens. And so as we're looking at this, we should have seen in that video that reactivity for nonmetals is going to increase as we move as we get to lower energy levels, as you're looking up on the periodic table. So fluorine was that most reactive of the videos you saw. And then this is asking, what direction is the reactivity trend across the row for a nonmetal? Well, if we think about that Coulombic force, fluorine has more protons than oxygen, so that Coulombic force is going to be greater, meaning that fluorine's going to have more charge to gain that 1 electron, but also fluorine is closer to the octet. It has 7 valence electrons, so it only needs to gain 1 more to get to that octet, where oxygen needs to gain 2 more with that. So our reactivity trend for our nonmetals is going to be opposite than our reactivity trend for our metals. I have a labeled periodic table at the end of these notes too that kind of shows all the trends on it. So you can label and add those to your periodic table. Now we're going to discuss, those were the trends from stations 1 through 4. We're going to discuss the trends that you saw in the pivot. If you haven't yet done the pivot, please make sure and do that, because we're going to just go through and summarize these. I'm not going to do a super in-depth look at them, but we will talk about then these rankings so that if you did those on your own, that you can check. And then going through these. You will need to do these CERs on your own using that information we have here, or that we fill in for here. All right, so station 5, which would have been that first station you did on the pivot, is atomic radius. So what is atomic radius? It's a measure of the size of an atom, the distance between the nucleus of an atom and its outermost electrons, so between those valence electrons. What you should have seen on that pivot is that atomic radius increases to the left and it increases down. And if you think radius of the circle, atomic radius is similar. If we have, here's my nucleus in green, I have whatever energy levels of electrons, if I just kind of think about this in terms of a Bohr model. Well, as I'm going down those energy levels, my valence electrons, if I have 1 here, those are pretty close. But then if I have, this shell is full, so now my valence electrons are in the 2nd energy level, that radius is going to get farther away. And so atomic radius is looking at what is the distance between the nucleus and the outermost valence electrons, so in that highest energy level with them. So if you haven't yet, think on your own what would explain this in terms of Coulombic force and our valence electrons. If you're ready to go on, keep going with me. Otherwise, feel free to pause the video and think about this. All right, so our explanation here as we're looking at the periodic table. So, and you can fill in that explanation spot on your lab document if you haven't yet. So our explanation for this, as we're looking at our rows, that atomic radius is going to increase from period 1 to period 7. And so that's us looking as we go down the periodic table. Because this one, our valence electrons are going to be in a higher energy level, which means that they are farther from the nucleus, which means we also have a weaker Coulombic force. And so those electrons are going to take up more space, meaning we have a bigger atom. As we look at those columns, group 8 to group 1. So as our columns change, so as I'm going from group 8 to group 1, so to the left on the periodic table, I'm going to have less protons for those elements that are in the same energy level. And with less protons holding that same energy level of electrons in, that Coulombic force is less protons, less nuclear charge, and so the electrons are going to be held less tightly, resulting in a bigger atom. So that atomic radius is increasing to the left and down. If we go through and rank these, remembering our trend here increases to the left and down. So looking at lithium, which is here, carbon, which is here, fluorine, which is here. As I look at these, all of these are in energy level 2. But which one is going to have that highest Coulombic force, or I guess we want largest side first, so least Coulombic force? Well, lithium is going to be my largest because it only has 3 protons holding energy level 2. Carbon then is going to be the next biggest, or sorry, next smallest, and fluorine is the smallest because it has the most protons holding energy level 2. Now if we go to the next group, lithium, again, sodium and potassium. Now these are increasing energy levels. Lithium is going to be, I'm largest to smallest. So largest now is going to be potassium because its valence electrons are in energy level 4. And then sodium, and then lithium is going to be the smallest because there are less valence electrons. And so those will be held closer to the nucleus. The Coulombic force is greater. This one, now if we're looking at sulfur and an ion of sulfur. So sulfur is here. If we look at sulfur with a -2 charge, let's consider what would happen to its electrons. Well, we would add 2 electrons, but our protons are going to stay the same. So what's going to happen to the size? Which one of those is going to be larger? Well, sulfur is going to have that set number of protons, 16 protons. What's going to happen to the size if we add more electrons? Well, sulfur with more electrons, sulfur -2 is going to be larger, but sulfur with just the normal number of valence electrons is going to be smaller. Last one here, magnesium. Here's my magnesium. And then I have magnesium with a +2 charge. Well, magnesium with a +2 charge, that means that we're getting rid of electrons. And so we're going to have less electrons, and that's going to actually decrease that energy level, even though our protons are staying the same. So our magnesium with a +2 is going to be smaller because it has less electrons, but same number of protons than that normal magnesium with that. If you want, pause the video, take some time to fill out that CER at the bottom on atomic radius, and then we're going to move on to the next section. All right, ionization energy is our next one. Again, we're going to go through talking about explaining these and then ranking them to make sure we understand what those trends are. Apologies about the bells. All right, station 6 was ionization energy. How much energy it takes to remove an electron. That trend should increase to the right and up. Take a second to think about that. When you're ready, we can go on to the explanation. And so again, energy it takes to remove an electron. We want to consider, does something want to lose that electron? For this one, as we're looking at our periods, it's going to increase from period 7 to period 1, that ionization energy. And so increasing to the left. Sorry, I did that wrong. Increasing from period 7 to period 1. So increasing up. Our valence electrons are in a lower energy level, so they're closer to the nucleus when they're up here, which means there's more Coulombic force. And so there's more attraction and more energy is needed to remove an electron. So, and again, energy needed to remove an electron, that's the definition of ionization energy. When we're looking at now the columns increasing group 1 to group 8, increasing as we look to the right. As we go to the right, we are going to have more protons in that same energy level, which means there's more nuclear charge. So that's increasing the Coulombic force, even though the proximity isn't increasing. So it's going to be more difficult to lose those electrons because of that increase in nuclear charge and that increase in Coulombic force. As we're looking at doing these CERs, you are going to also need to include what is that definition of ionization energy to explain when you are maybe comparing ionization energy for 2 elements. All right, now let's rank from highest to lowest ionization energy for these elements. So looking at GE, which is, so we've got oxygen, phosphorus, there we go. Those ones there. So from highest to lowest ionization energy, if it's helpful, drawing that trend. We're looking at these here. Ionization energy, it is going to take, so highest ionization energy to lowest. Oxygen is going to have the highest ionization energy because those electrons are closest to the nucleus. It's going to take more energy to remove those because they have a higher Coulombic force. And then we've got phosphorus, and then GE. Carbon, nitrogen, and silicone. Carbon, nitrogen, silicone. As we're looking at those, well, lowest ionization energy is going to be silicone because it is in energy level 3, whereas carbon and nitrogen are in energy level 2. Then if we're comparing those ones, nitrogen is going to have that highest ionization energy because it has more protons than carbon, and then carbon is in the middle. Last one on these, we've got our chlorine, bromine, and gallium, which is right here. Again, we've got a couple things to look at. So looking at lowest ionization, or highest to lowest, well, chlorine is closest to the top left, so that's going to be the highest. And then we're going to have bromine, and then gallium is going to be the lowest ionization energy there. All right, one more station, electronegativity. This is tied really closely to ionization energy. And so with our electronegativity, that definition is the measure of how strongly atoms attract an electron. So thinking of, it's kind of the opposite of that ionization energy. Ionization energy, how much energy it is to remove an electron. This is now how strongly atoms want to attract electrons. So that need or that desire for those electrons to reach an octet. That trend increases to the right and increases as we go up. And so the definitions of electronegativity and ionization energy are opposite, but their trends are the same because they're just describing the process differently. So with this one, that explanation. So it's increasing from period 7 to period 1. So increasing as we move up. Again, as we go to a lower energy level, there is a stronger Coulombic force, which means you have more force to attract other electrons. So that gives you a higher electronegativity. For our columns, this is going to increase from group 1, this should say, to group 8. So increasing as we go to the right. And again, with this one, more protons as we move left to right. So more protons, which gives us more nuclear charge in that same energy level, which increases our Coulombic force. And so then that Coulombic force, that attraction of electrons, is going to increase as well. And so fluorine is our most electronegative element, and fluorine is right here in the top left. So take a minute and consider, why wouldn't it be helium? And if we think about it, it makes sense that noble gas would not be included, because how strongly atoms attract an electron. If we look at any of our noble gases, those already have full outer shells. They have the valence electrons they want, and so they don't want any more electrons. They're not going to attract any more, which makes fluorine our most electronegative element. All right, last step in this is ranking these in terms of electronegativity. Lithium, sodium, potassium. We've got lithium, sodium, potassium. So most electronegative to least electronegative. Well, as we're looking at these, lithium is going to have that stronger Coulombic force, so it is going to attract electrons more. Sodium, and then potassium. And again, if we want to draw our trend on our periodic table there. Next, we've got that GE, phosphorus, and oxygen. Looking at those, oxygen is in that closest to the top right, and then phosphorus and Ge as our least electronegative. Electrons are farthest from the nucleus, so the Coulombic charge is less, and it will attract other electrons less. And then lastly, carbon, nitrogen, and silicone. Silicone is in a highest energy level, so it's going to be the least electronegative. Nitrogen is going to be my most electronegative because it has the most protons in that energy level with carbon, and carbon would be in the middle. All right. If you haven't yet, take a minute and label those trends on your periodic table. We've got that reactivity trend for nonmetals, reactivity trend for metals, atomic radius, electronegativity, and ionization energy. Those are all trends you will need to know for your upcoming test and that you will use when you are completing your periodic trends lab assessment. Next steps, go to that lab assessment on Schoology. Make sure you are reading the directions provided by your teacher so that you know if it's resumable or not, and that you have 2 attempts to complete that. Reach out with any questions.